Sorry, Jack, I forgot to give you the paper. Let's do it.
I'm in the first person, thank you.
All right. So you guys spent a couple of weeks gathering the data, and then I spent a ton of time looking at those data. And so today I want to take you through what we did and why we did it. First off, Pauling's paper is all about the functional response, and I reminded you yesterday what the functional response is. What is the functional response? Okay, let's
I'm just like getting sick, yeah, it's fine.
So relationship between prey density and predator success.
So in each of these figures that you have in front of you, prey density is on the x-axis from none to 256 disks available for sampling from, and the number of disks captured is on the y-axis. This is the equivalent in a classroom setting of the number of prey that are killed and eaten. And so when you look at these figures, it's the number of disks collected versus the density for each of the different methods that you used. In some cases, you search for sandpaper disks with your finger. In some cases, you search for sandpaper disks using a pencil. In some cases, you look for transparency disks, both with finger and with pencil. In some cases, we had you not collect the things that you found. We had somebody else collect them, which got rid of handling time. And in some cases, we clumped the prey spatially so that they occurred in little patches. And in other cases, the disks were distributed evenly around the tabletop. And so what we basically did was we manipulated a couple of fundamental things. We manipulated handling time. When you were searching with your hands, how would that handling time compare to searching with a pencil versus searching for, searching with your finger versus searching with a pencil versus not having to handle the prey at all? Which of these would have the fastest handling time and the slowest handling time? Okay, so not handling, having somebody else pick up the prey for you would be the least amount of handling time. What would be next? Finger would be next, and then what would be next? Pencil, because I asked you to collect the discs with the hand that was also holding the pencil. And so in what way is handling time going to affect the relationship between prey density and the number of discs captured?
It's gonna reduce the number of disks captured.
So as handling time goes up, the number of discs captured should go down. So for large handling time, you might expect gains to come fairly quickly, but handling time would then begin to put the skids on things, because for more and more prey that you have available, you catch more and more prey, which means that you're catching more prey, but you're also spending more cumulative time handling those prey, as opposed to if there is no handling time at all, your prey capture is proportional to the number of prey that are available, because you're not spending any time handling. Another thing that we affected was the detection probability. How did we do that?
By either increasing the disks or switching to the clear disk.
So this was the difference between whether we're doing sandpaper discs versus transparency discs, because the transparency discs felt kind of like the tabletop in many ways. How else did we affect detection probability? Finger versus pencil. So if you can detect things easier because you're either searching for sandpaper discs or you're searching with your finger rather than with a pencil, your rate of prey capture should be higher than if you're searching for transparency discs using any method, or if you're searching for any kind of discs using a pencil rather than a finger. So we manipulated this, and the last thing that we manipulated very briefly and not very thoroughly was prey distribution, where we had prey that were uniformly distributed versus clumped, spatially aggregated prey. And this was the last thing that you did. What would the effect of clumped prey be compared to uniformly distributed prey in terms of this, once again, gain of prey items as that varies with density?
As clumping increases, number of discs captured probably increases.
Would it increase or would it decrease? So imagine that you have a clump here, a clump here, a clump here, and a clump here. If you're searching around and you miss a clump, you just don't ever find anything. And this was true. If you go and look at the data, especially at low prey densities, in the clumped data file, there were many more of you who found 0 discs at like density of 4 and density of 8 and density of 16, because you just bopped around, you never stumbled into one of the clumps. Now once you get to one of the clumps, what happens? You tend to concentrate your searching in that area until you think you've collected everything in that clump. And then once you think you've collected everything in that clump, you start going looking for another clump of prey. Once you get so many discs on the table that there are clumps everywhere, what does it start to look like in terms of prey gains?
Exponential.
Well, not exponential, but it looks just like a uniform distribution because the clumps are all really big and they're separated by relatively small distances between clumps. And so these patches have more of an effect on prey capture at low densities than they do at high densities, because at really high densities, it was, you guys remember this, it was very hard actually to create spatially aggregated groups that were separated from other spatially aggregated groups when you were at 256 discs per 9 square feet than when you were at 16 discs per 9 square feet. And so typically what happens in a clump situation is at low densities you experience relatively poor success, and then that success increases at higher densities. That begins to look more like a typical functional response curve. So you get this sort of S-shaped curve. Now, we didn't observe that in this case. If you looked at the figure for clumped prey, you don't see a curve to it, but part of this is that at that lower end of the distribution, there aren't huge differences in the number of sandpaper discs that are there. But what you do see, if you look at the top right figure on your paper, is there at the beginning, you don't see nearly the amount of gain early on that you see under the type 1 scenario where there's no handling time. So there is something of a slowdown here at the beginning before it starts to pick up. But then once you get up to 16, 32, etc., it picks up pretty quickly. But in the case of clumped prey, your overall rate of gain is lower than it is when you don't have any handling time at all. So So your paper basically needs to follow these specifications. So you guys asked me what the literature review for this paper needs to be. It needs to be 3 papers, because I went back and I found stats. So you already have Halling 1959. You need to find 2 other papers that talk about the issues that are involved in what you did, which is the effect of handling time constraints on prey capture, the effect of detectability of prey on prey capture, and the effect of the spatial distribution of prey on prey capture. Halling talks about all those things in his paper. We've talked about them now a couple of times, although this is the most formally that we've talked about them in lab. So you need to explain what a functional response is, why they're important in studying predator-forager behavior, and factors that lead to different functional responses. We've just talked about that to some degree. You include in your review of the information in Spec 7 3 papers that have been published since Halling that shed light. Oh, so it's 3 papers since Halling, so you have Halling, find 3 more that have been published since then. I would find 1 on handling time, I would find 1 on detection probability, and I would find 1 on spatial distribution if I were making the most of my effort in here. Make sure your paper is factually correct. In this lab, you alter things about the way in which you forage, so you should craft a set of hypotheses about the characteristics of forager prey. It changes the shapes of functional responses based on literature reviewed in the introduction. We just went through what those are for you here. So this is basically building for you the beginning of your introduction. What are the kinds of things that affect functional responses? Well, handling time constraints, detectability, probabilities of the prey, and whether or not prey are clumped or more uniform in the environment. Flesh those things out. Create a set of hypotheses and predictions that go along with the factors that you varied in this set of experiments. Just make that complete. Your methods, they need to be clear and straightforward. The first time you describe the methods is going to be pretty detailed, but then when you switch from searching with finger to searching with a pencil, that's an easy transition, and then changing sandpaper disc to transparency disc, that's an easy transition as well. And then distinguishing between uniform versus clumped distributions and how you remove handling time. So once again, methods should just be complete enough that somebody would be able to reproduce those things. We're going to go through the statistical methods that we used today, so you'll have that under your belts. I am recording it at Kennedy's request. Your results, clear and well organized. They include references to figures and statistical results. The R script that I have for you will reproduce all of the figures that are sitting on your table right now.
Will you email us the figures?
What's that?
Will you also email us the figures?
Why on earth would I do that when I can make you do it in R?
Why would you make us do that? Look, I get that you like R. I don't like R.
So it should have an introduction, it should have methods, it should have a discussion. The discussion basically will deal with what did you find in your experiment. One of the things that you're going to find when you go back and look at Halling's 1959 paper is that his curves differ somewhat. So I brought a copy of Halling 1959, and one of the things that you're going to find is that you guys collected many more discs than his students did. And it's not because you guys are brilliant, it's because we actually conducted our experiment differently than his. So the methodology that he used, we've adapted somewhat to our environment here at Jewel. What are the differences between what he had his students do and how you guys went about it that has resulted in something of a difference between what your results are and what their results were? That has everything to do with handling time. So reread Halling's paper, look at his figures, ask yourself, how do his figures differ from what our figures look like? What was fundamentally different about the way we did things compared to the way they did things back in the late 1950s that has led to a difference in the way our data turned out? They're qualitatively similar changes as you go from one type of doing something to another type of doing something, but our quantitative data don't fit his quantitative data at all.
Do you want us to discuss that in our
Yeah,
report?
yeah, it says that explicitly. Thought it said that explicitly. Oh, it doesn't say that explicitly. It does say it's clear and organized and comments on both the original hypothesis and the nature of observation and bias. There's a portion in there about observation and bias where we did something different than they did, which actually fundamentally changed what we found compared to what they found in terms of the shapes of these curves, how steep they are, how many disks you ultimately captured, et cetera, et cetera. You'll figure that out when you go back and read Holland more carefully. Then there are writing standards. So your discussion doesn't have to be terribly long. Your introduction should be long enough to accomplish these tasks, describing what this is, describing what the 3 different types of functional responses are, and describing what about these things changes one functional response type into another functional response type. And then in your hypotheses, you should explain how what you did would be predictive of different types of functional response. And I think as you do your introduction where you describe the different kinds of functional responses, you'll see how the manipulations that we did translate into either a type 3 functional response, a type 1 functional response, or a type 2 functional response. So that is the assignment. It's due after spring break, which means you have plenty of time to work on this. Now, we have to deal with the R script from hell. So this thing is 747 lines long. It has some peculiarities that I have not had to deal with in past years because some of you guys submitted freaky data, and I'll show you what that's about. So in R, you should be running this out of RStudio. If you have it open, so those of you who have computers, do you have R open? R, you got the script up and running?
Does that mean we just click the file that you put?
Click the file, it should open in RStudio, and it did exactly that. So just click on the file and it should open. So you need to copy the files into a common directory on your computer.
Okay.
So these instructions are on Moodle. When you get to Moodle and you find today's lab materials, there's a folder there. It has a bunch of files in it. You need to download all those files and copy them into a single root directory so that all the files are in the same folder. Open the R script from that folder. When you do that, R will know that you're working in that directory, and it will have all the data in that directory, so you won't have to tell it to go and find the data someplace else. Did you get that open and loaded?
When you say save it to a single directory, is downloading the folder just accomplishing the same thing?
It might if you're just downloading the folder.
That's what I'm doing.
So close RStudio. Now go to wherever that folder is on your computer. Now open the R script from there. And then
So
RStudio.
you want us to save what to what?
Save all of the files that are in today's folder on Moodle to a folder on your computer. The whole thing, wholesale. So what it should look like on your computer is wherever you saved this stuff to, there should be a folder, and in that folder should be the R script as well as all of the data files in the same folder somewhere. This is a folder on my computer that is called Hauling Disk Data 2020, and inside of that folder is the script as well as all the data files. And there should be 6 data files because we have 6 different figures on our outputs.
Is this the thing? No. This is not.
No, you're opening R. You're opening base R. Yes, it opens base R.
Base R.
installation package.
Uh-huh.
Should you have all of your stuff?
I don't know how to do organization.
It's like 45. How did that get on your desk?
It just opened when I hit download
There you go.
on the internet, so. And I pulled that over and stuff because I thought that was what it was supposed to be.
It hasn't really downloaded. Where's the downloads?
I think that one for Mac. I didn't know if that was the right one. When you're weird requiring two fingers to right click on it. First, drag that into your applications folder. I don't think it's going to work. That's where applications are. Is yours working?
When I click on it, like I said, something with, RSU and then it says more finance.
This is why things are tough.
Oh, you're already.
You might use this version, yeah.
You don't have Base R. You need R. So R Studio is just a graphical user interface for work on some laws. So you need to go to, type in CRAN, C-R-A-N in your browser. Latest version.
If we open that one file that I had Juice look at, do we have to still save all those other files that you posted on Moodle?
Yeah, because those are the data.
Apparently I need to pick a different one.
You should be able to get it. Just go again.
Well, this one says it's not gonna work on Mac because I don't have like whatever.
What does it say you don't have?
I don't have 10.12.
Oh, then go to an earlier version. That's the problem. Although you should have, you have you have El Capitan, you don't have Catalina. Yeah, go back to whatever. So go to about your computer. Okay, go up here. Yeah, 10.11. So find the version here. Update that.
I'm old, I bought this a long time ago. So that says 10.12. But now I don't know. So I can't do these things.
Four, and I'm
We'll
just
be- we'll
spitballing
just be
here.
old school.
You could just email us the correct.
Yeah, you're working, so you're gonna run code here, and the run code is gonna appear over here. And it's gonna output graphs into a separate set of files that will just magically appear on your computer, but that'll be
Is
fine.
this done now?
You're running, yep, this is where you're gonna run things from. Whenever you want to run a line of code, you need to click on that, except that you don't have that library installed, so you need to go to install packages and on this. So when you do that, it's installing that, and then you're gonna have to do the actual ggplot, which Martin has to just copy this and then change the name over here from Armisk to ggplot2 to Arcmass as yeah, you're not gonna be able to do this right now.
Okay, great, perfect. I'm proud of me.
And you're up and running. Yeah.
I can't get my ggplot package to install properly. The other ones would want to.
Logan just
Says
says
I
as if
need
like,
this,
it's just
and then I
something he
click
does all
install,
the time.
and it'll run for a while, and then it'll say like lazy, or download failed, or something like that.
How do I update this computer?
Just go to your settings.
It's just telling you it's done. And when you go to things that you have to do yourself, you should see some it's just trying to run ggplot. Sometimes this also helps just close it.
There's usually like a little box.
Yeah, like a
spot for it.
that's, yeah.
Like,
Well,
you know what I'm talking about?
it's really, this computer really didn't know when I got it when I graduated high school.
Yeah, that's
It's like
cool.
2016.
See if you can go to that Apple. See if it's like software update.
You're smarter than I am.
What are those?
I don't know what's going on with you.
What the heck? No, that's happening. Yeah, go.
I don't know. Why hit them?
I shouldn't be allowed to have a computer, honestly. Like, I'm using it at like 20% of its functional capability because I have like no idea how to do important things.
You should look it up. You have to like download the name. But it says the, I don't know.
Yeah, you should be able to just Google.
Yeah, something's stopping the download.
I ruined my Google. I got a virus, so that every time I pulled up Google Chrome, it said me no at the top, and then I would Google something and I would search it in vain. It took me like 4 hours to get this virus off my computer. I
Yeah,
should
that
go
might
into my
be
like
it.
computer's like.
So you're gonna be able to do everything, the only thing that you're not gonna be able to do is you're not gonna be able to generate any of the graphics until we figure out why it's uploading that. All right, everybody who can work is working, is that correct? Okay, so those of you who, when you get to your computers and open up this R script, you're gonna see that I have squunched it. Squunch is a technical term in R. Basically, it's not, I made that up. Basically, R runs off of packages. And so you can at any point see which packages you have available to you by clicking on the Packages tab. And you can see all your packages here. And for example, for this particular script, I need to have 4 packages. RMISC, which just has some miscellaneous data analysis tools in it. ggplot, which allows me to plot things. Car and mass help me run regressions, which is one of the things that we're going to have to do. So the first thing that you have to do is you have to get all of these things activated. So for example, if you look down my list of available packages, you will see that, for one thing, I have too many in my library. You'll see that ggplot is already activated because I've been working on it all day. But if I deactivate it and I run this, what it does is it loads the library. And anytime you run a line of code in this panel, the running of it actually appears down here. So I've loaded library RMISC, and it's giving me the command prompt asking me, okay, I did what you wanted me to do, now what do you want me to do next? I will load ggplot, and when I load ggplot, you will see that ggplot will get a check mark over here when I run it from over here, telling me that it is loaded. And so I ran ggplot, what do you want me to do next? And you see that ggplot is now checked as being active in this session. I run car, I run mass, all of those things loaded fine, mainly because they were already loaded. But anytime you activate something up here, the running of it appears down here, and whenever you get a command prompt back, it basically tells you, I did the thing that you asked me to do, I did it successfully, what do you want me to do next? If you get an error message, the error message might be, I tried to do what you wanted me to do, I couldn't do it, and now I can't do whatever you want me to do next. I'm giving you a command prompt so you can ask me to do the thing that I just tried to do for you again. But if you ask me to do the next thing, chances are you're not going to be able to do it. So some error messages you need to pay attention to because it's telling you that R couldn't do something that you asked of it. Other error messages are just informative, saying, hey, there's this weird thing that I saw when I ran that thing for you. You should be aware of it, but it might not be a problem. Learning the difference between those two errors takes a little while, but we're actually going to encounter some of those errors, and I'll show you the difference. So the packages that you have are available and up and running. Just to save myself some lines later in the script, I will oftentimes set up a formatting block for how I want to format my graphs. So this is just a formatting block that tells you that I want the plot title to be centered above the plot. I want the plot title to be a certain size font. I want the x-axis, y elements to be a certain font. The y-axis elements, the x-axis elements, the axis text, et cetera, et cetera. These are all just fonts. I want you to get rid of any weird grids in the background of it, and I want you to get rid of the gray panel, which is kind of our standard thing. So I just want a plain white graph with dots on it, with fonts of certain sizes. And then this thing here, for those of you unfamiliar with R, this is called the assignment operator. It's used whenever you want to take this and call it that. So the assignment operator basically says, take all this crap, and whenever I type th, call up all that stuff. So I don't have to keep copying that over and over again. If I ever want this, all I have to tell R is th, and it will give me this. So it basically, the assignment operator, which is this thing, basically says, take this stuff that is on the right-hand side of this operator and call it that. So that whenever I want this, all I have to tell R is that, and it will give me this. So when we do that, it's now done that, and it's just storing it. If I ever want to call that up again, I can just type th, and it should give me that. And it doesn't look the same, but it's got all the same information.
I could actually do this instead. Tell it to print that. Well, it's actually not doing that. Okay, so forget that. But we'll see where this comes in a little while. So the other thing is hashtags, #, if you wish. This is how you comment things. So any line of code that you have a hashtag in front of, it's not going to run that. It's going to treat it as just text. And so I use the hashtag to comment things. The other thing about hashtags is if you put 5 hashtags in a row, 1, 2, 3, 4, 5, it allows you to collapse that. So you see the line number skips from 24 to 135 because we need lines 24 to 135 to run the analysis that analyzes finger sandpaper data. Then 135 to 271 runs pencil sandpaper. 271-400 does pencil transparency. 574, finger transparency. 271-400 does pencil. 271 to 400 does finger. 400 to 517 does pencil, et cetera, et cetera. You can click on the purple box, and when you click on the purple box, it opens that up. So now you can see all of the lines of code, and these lines of code will be available to you until you get to the next bunch of code that is all grouped up in Squunch. So there's a little gray box, a little gray margin over here. If you double click on the gray margin, it will recollapse that thing that you just expanded. So now finger sandpaper is all squunched again. You can also just click on the little arrows, and that will do the same thing as clicking on the purple box. So starting with finger sandpaper, leaving everything else squunched up so that we don't get confused, because anytime you have a script that is almost 1,000 lines long, you want to avoid confusion as much as possible. I always try and keep file names simple. So I have abbreviated everything as FS for finger search, or finger sandpaper rather. Finger transparency is finger transparency. FT. Pencil sandpaper is PS, so this is pencil, sandpaper, et cetera, et cetera. Finger sandpaper type 1 and type 3. So these are the four files, and their names are relatively simple. So the first thing that you want to do is you want to get the data file that is on your hard drive, you want to get it into R. So we're going to start with finger sandpaper search because that's the first thing that you did. This reads the file in. Once again, this is an assignment operator, which basically says, I want you to read in a CSV file, which is this file, and I want to give it a shorthand code, FS. So this brings this into a data frame called FS. So anytime I type FS, it will just give me that data file. So this next thing is called head FS. It gives us the first 6 lines of the file, so we can verify that it actually read the file incorrectly. And so what it does is it just returns to you the data file. It's got Claire's data first, the density of disk, 4, 8, 16, 32, 64, 128. It doesn't give you 256 because that's the 7th line of the file. It gives you the number of disks recovered, and it gives you the handling time that was observed. Those handling times seem long to me. Why do those handling times seem long to me? So in I don't know, I'm gonna have to go look at that. That seems not right to me. One would think as much time as I spent with these data files that I would have noticed that prior to now.
Did you just put enter by headfs to get it popped up in your directory? Or is that not called a directory? The working area?
Oh, this history up here? This thing? No, what?
How did you get
In the
there to
console.
pop up like that from headfs?
This?
How do you do that?
Oh,
it's command enter or command return.
Okay.
So on a Mac to run a line of code, it's command return, and on a Windows machine, it is control enter.
So if it says the object isn't found, how do
Yeah.
we link our data?
Object isn't found, it's because you're running R in one part of your computer and your data exists in another part of your computer. Which is why I told you to put the R script and your data in the same directory and open the R script from there. If you did that, so first thing at the top of every R script that I have is get working directory. It tells me where R is working from. On my computer, it's in users, it's in my username, it's in this class's animal behavior stuff, it's in R scripts and data, and this is the subdirectory under that. So getwd will tell you where you're running from. If you're running R from someplace other than where your data are, R doesn't know where to go and find your data.
So click command enter.
Yep. You're running R from downloads for some strange reason.
So
That's where the file directory downloaded to.
I've got
So where are your data files?
saved on Google Drive.
Yeah, it's not going, because you haven't told it, actually R doesn't have the capability to go to your Google Drive account and find. Why are you saving everything to Google Drive when you have a perfectly reasonable hard drive on your computer that you could save things to?
Because that way I can access it on my iPad or whatever.
Okay, fine.
From a different computer.
So you need to, so you're.
I'll save it to my downloads, but once I do that, how do I get that to actually enter into here? So like say it's saved on my downloads.
So you can, so where is your data found?
In a folder on Google Drive.
Okay, go to that folder on Google Drive, click on one of your files, right click on one of your files.
Okay. Did that.
Now go to get info for that, since you're working on that.
Okay.
And when you get info, it should give you a path.
Yep.
Copy that path from users down to the end. Copy that? Copy that.
Okay.
Now go to this section here. Right under getwd, type in setwd and an open parentheses, and then it will just give you a pair of parentheses. Paste that path into that thing. Now, it's probably going to look weird. So, oh no, it's going to look fine. I think you need to have it in. Now, take that whole thing that looks kind of like this but has different information, put it in quotation marks at the beginning and end, and then execute that line of code.
So put it in quotation marks up here or in the console?
Up here. See how it's giving you an arrow?
So quotation
Yep.
marks.
Nope, nope, before the hash. There, and then at the end. Now it's getting rid of that. Now run that line of code. Okay, now run getwd again.
Same thing.
Yep, that's right. No, just run that line of code. Command enter. Now what it should say is users jack Google Drive animal behavior. You have basically said, I'm running R from one place in my life, but I want you to go get data from another place in my life. You just told it where to go get it. Now when you go down to the translate that data file, it should help with
Right here.
Yep.
I'll move it to my.
The problem is that you're operating, your
with Google Drive.
Your Google Drive isn't actually resident on your computer, it's just a link to something that's on the web. So you just need to get those things on your computer. I realize that you think that you're being all modern and efficient by
No,
putting
no.
things on Google Drive, but in some ways, if you're trying to do real things, it doesn't really work.
I just do it to work with the needs that I have.
I understand an issue with not found, like you said.
Yeah, it's because you're running around in one place and your stuff's in the other
But
place.
it's here, I know.
Once again, that's not actually on your computer, it's somewhere out in the internet, you need to get it on your computer.
What is,
computer is hooked to the internet, as soon as I disconnect your computer from the internet, you won't have access to those files anymore. You need to get it physically residing on your hard drive on your computer. I realize it looks like it's on your computer, but it's not. It's in the cloud. That's the nature of cloud computing and cloud storage.
But they're downloaded to my computer though.
Where?
So if I mean, I'm not gonna do it, but because it would shut this off if I can disconnect the Wi-Fi.
Why would it shut that off? It shouldn't shut that off if that thing is actually on your computer. You just made my point.
But I still have access to everything on iCloud without Wi-Fi.
Okay, then you're not having access to something somewhere.
Yeah, I know, that's what I'm trying to figure out.
Is that just
Okay, so
my things?
where is your R program?
Our
That's the
program.
cloud.
Where is it? Where is it?
If you get like multiple devices,
Downloads.
saves
Okay, so where is your data?
Is that why my photos from my iPad just randomly show up on my
Okay,
phone?
so you're running
Yeah.
R for one place,
So they have to.
and your stuff is someplace else.
That means
Running
that,
this.
So you have to either tell R where your stuff is located that you want it to work on, or you have to put all that stuff in the same place.
Well, I'd rather tell it.
Either of those work. You have to now use setwd to tell it where to go and find those things. And if it's on your iCloud device, if it's on your iCloud storage, it might or might not do it. It didn't do it.
You just literally type iCloud.
No, you have to get the path. You have to go to where your file is, get info, and it will give you the path. So,
Oh, I see. From get info.
the issue isn't that you have difficulties with R, the issue is that you have issues with computers. So if you go and get info, under where up here, it says where is this file? So I right-clicked on the file, I got get info, and it tells me where it is. It's in users Glowinski P 2020 Bio 357 animal behavior, R scripts and data 2020 hauling disk data. That's where my file lives on my computer. If I'm not running R from there, I need to tell the computer where my data exists so that R knows where to go and find it. And you do that by giving it the path to your data. This is just a written out line of instructions that is like a physical address to where the data are on your computer. You can copy that directly into the setwd command, and it will reset your computer. So if I copy this whole thing in quotes and plug that into setwd, it will now say, okay, the stuff that I want R to work on is there. Do that. And it will work.
Conversation's really stressing me out.
Oh, nobody's more stressed than me.
No, I am more stressed than you.
All of you should have some basic knowledge of how your computer works. Unfortunately, you were brought up in a world where computers are basically beige and silver and black boxes, and you've never actually gotten into the inner workings of your computer, so you don't realize that your computer has a structure to it. There's a hard drive. It's a physical thing. It doesn't exist in the cloud. And you can basically divide that up into whatever little segments that you want. You can store information there physically. But when you store information physically there's an address to find that information. That address is a path. And if you want to find that information, you either have to be able to see the folder, but you can actually access anything on your computer without ever actually seeing those folders. All you have to do is know the name of it and where it is that it's located. And back in the old days, we used to have to either carry around these paths in our heads or we would write them down in little books so we would remember on computers that didn't have graphical user interfaces where our stuff was stored. Because I grew up in a time before graphical user interfaces, I still think about computers in this way because you've never seen a computer without a graphical user interface. It's very difficult for you to think about computers in this
Like
way.
graphical user interface, you mean my desktop with my folders on it?
Yes, yes.
Ah.
That's it exactly.
So I save it to my desktop and then still run this.
It's still there, it's connected
Okay,
to power.
close R.
Download it.
Go to the place on your
It's
desktop.
on 93%.
So you haven't closed R yet.
But is it gonna die when 16 minutes?
Just right.
Yeah, so we're still running from wherever you were. Go to wherever all your stuff. Lose all your stuff.
You're really charge.
And what's gonna give you my
on your desktop? That's fine. Is your R script also there?
My R script is on my down.
Drag your
What is yours?
drag your
Oh
R
my
script
God,
onto your desktop,
Claire.
open it from the desktop.
I'm not really sure.
And then when you run GitWD, the last thing on your path is going to be desktop. When you run Git working.
Have you got yours worked
I feel like, I don't know, could you check one?
Sure.
But this is
Do you,
your
do you, do you think it's working?
I think so, I know, the set, I think I figured it out.
The rest space is a break.
Yeah.
God bless.
You just set your working directory.
It's a GG plug.
Is it ready?
How did you get this?
Anything will happen. This is in downloads and my.
Yeah, I don't know, man.
I'll treat them like this stuff.
And it should be running downloads.
I haven't detected today.
No. Although definitely it's not.
Show me.
This is the bit in progress users chat.
Show me.
Oh no, what just happened? I think I just broke my computer.
Probably good at this one. I would have thrown that thing. This version looks so sad.
I don't even know like about the versions of things. I just don't. I
You're in
haven't
the downloads
cracked that world.
You were opening that script from someplace else.
Okay.
Now try and scroll down here.
I just like got this
Now
like.
try and load it.
Oh.
Learning?
It loaded it because of your script and your
Yep.
data now. Okay. Is everybody who can be up and running? Oh, yours are running, but you're running in BaseR. That's ballsy.
I'm not because we couldn't get to figure it out. I'm downloading the update on my computer right now.
We couldn't get our studio to work, but you were running BaseR just fine.
Nuh-uh, because then you were like, no, you're not gonna be able
I
to
put
do
it like in
this.
a file.
Like we clicked something and then you were like, oh, and then I was like,
We couldn't do our studio, but you still have BaseR working.
Yeah, but
No, your computer is now unavailable to you because you're downloading a new
I'm
operating system.
downloading the Catalina.
All right.
Claire needs
Alright.
probiotics.
It's good, I'll just figure it out. I don't know.
You're not figured out yet?
I don't know, I think it was how I saved it maybe.
She saves for like just downloads. And it's like,
So don't do that.
If it's all in downloads, open it from downloads. If all your
What is
stuff
your
is in
downloads?
downloads,
How do I know I need
So now this looks like a crazy list of like random crap.
Do I hit open?
a lot required for that?
How do you organize such
In
things?
all the Excel sheets, there's like a Hauling script file with the R
All
Studio.
the others.
So do I hit that?
hauling, yep, it
Yeah.
should be hauling disk 2020, open that, and it should open up that script. And if that is in your downloads and all your data are in your downloads, it should run everything. Now the bad thing, everybody should listen to me, because this actually became a problem. I teach applied stats every other year. 2 years ago when I was teaching applied stats, I was having the same difficulty with one of the students in the class. And I said, the problem is you're running R in one place and your data are stored someplace else. And I said to her, where are you running R from? Like, where did you open this up from? She's like, I don't know. I'm like, okay, where do you store things on your computer? And she said, well, it's in my downloads folder, probably. I'm like, okay, let's go and find it in your downloads folder. And literally, her entire life on her computer was stored in her downloads folder because she downloaded things, and then that just became kind of her default directory for where things go. And like everything was in her downloads folder, and it was gigantic, and it became almost impossible for her to find things. What she got used to doing is using like Spotlight search or something like that, which then searched her entire hard drive, but all of her stuff was in her downloads folder. I taught her about directory structure of computers and how you can put things in folders that have, you know, useful names on things. And she spent the whole next weekend going through her downloads folder, making a bunch of folders on her hard drive, which is basically partitioning your hard drive spatially, and dropping stuff into there. And she came back the next week and she's like, oh my gosh, my life is so much easier now because I can now finally find stuff on my computer. If all of your stuff is in your downloads folder, that's not a very efficient way of going about things because it makes it difficult to find things. And especially when you're using a program that calls on other data files and things like this, it becomes really crippling because you don't know where things are. Now, if you just put everything in your downloads folder, it's going to be fine. But when you start outputting graphs, those graphs are going to be output to the same directory that you're running in. And so if you're running out of your downloads folder and all of your data are in your downloads folder, any graph that you produce is going to be output to your downloads folder, and good luck finding that graph when you want it. Because it's in this big slush pile that is disorganized and has everything in your life in it, and it's just going to be very difficult to find it.
Is your desktop on your downloads folder?
So my directory structure is this. Those are my folders. I have a folder for my old animal behavior class, my old applied stats class that has materials that I'm using that I migrate to my new animal behavior folder and my new applied stats folder. I have an old bio 233 and 259 folder because I was using those last semester. I have faculty meeting notes from this academic year. I have assessment data that we're using for assessment in the biology department. I have desktop, I have documents, I have downloads, I have a Dropbox. A lot of my stuff is organized online in a Dropbox. This is essentially my OneDrive or my iCloud. This is cloud storage. I have a folder for my home improvements. I have a folder for downloads from my iPad, which is where I download videos from. I have movies that is empty. I have music, which has music. I have pictures, which is sort of empty. I have Science Olympiad materials. These are the folders on my computer. And then when I click on stuff, if I need animal behavior stuff, I just click on the animal behavior thing, and then I have that is also subdivided into a bunch of folders. I need to easily access my PowerPoint so that I can find what I'm doing today in lecture. I need to find scripts and data. I need to find exams. Now I've told you where to find my exams on my computer. Sweet. Don't break into my office. Bean Lab reports, for those of you who submitted Bean Lab reports digitally, they went into that folder once again so I can just find them. So I had to download those from emails where you sent them to me. I had to drag it over, but rather than drag it in my downloads folder or drag it onto my desktop, I dragged it into a folder in my animal behavior folder labeled Bean Lab report so that when I go and get Jack's Bean Lab report because he refuses to give it to me hard copied on paper, I can go and get that thing hard copy. I'm just giving you shit. So I do it so I can find stuff because life is too complicated to spend all your life searching for files when you can actually just store them in a way. Think of it like a bureau. You have your dressers. You don't take socks and sweaters and t-shirts and pants and put it in one chest of drawers with one big drawer. And you pull out that big drawer and you're like, I need my green socks. Start throwing stuff out until you get to the green socks. You have a sock drawer, an underwear drawer, a drawer for t-shirts, a drawer for sweaters. Same thing on your computer. Think of files, or think of folders as just little drawers where you put things that are all together so that you can go and find them. And it's really going to make your life easier.
Computer might be beyond repair at this point.
It's not beyond repair. Everybody's, and I get to a point in my life sometimes where I have to just sit down and take an afternoon and rein my computer in because it's gotten cluttered. My desktop has too much stuff on it. I use desktop for temporary storage of things. Sometimes I forget to then go and remove them once I'm done using them and putting them back where they belong. And so there's a time when I have to go and declutterize my computer because it becomes difficult to find things. And so you should get in the habit of maintaining your computer in this way. Caleb?
Did you teach R script, the applied statistics class?
Yeah, we're using bar in there. We're using it every day, virtually every day. Yeah, the things that I'm telling you today, I told them like 5 weeks ago. I've had this conversation one time, so I care.
All right.
Anyway, rein in your computer, don't do it today. It's too late to do it today. If you need help with getting R running, if you need help with kind of how you can organize your digital life on your computer, come talk to me. I can offer you some advice and actually help you go through the mechanics of doing it if you need to. What we need to do today is we need to look at data. And in order to look at the data, it would be nice if your R script was running, but it doesn't have to be because my R script is running. All right, and this is all on video, including my rant about digital clutter. So, when you get R up and running, you're going to try and activate these libraries, and it's going to give you errors saying that package doesn't exist. Go over here to Packages and click on Install, and when you click on Install, if you don't have RMISC, when you start typing in RMISC is going to come up in the list of available packages. Click Install, and it should install it without issue unless you're loading. In which case,
I get that much.
well, so he's having trouble loading ggplot, which is the plotting program, the graphing program. If you're having trouble installing a package, come and see me. I suspect I know what the problem is with you not being able to run that. If you get all of your packages installed, then you're good to go, and you can move to the next thing, which is basically loading up a standard formatting block. I use standard formatting blocks so that when I'm working on a project, all of my graphs look the same. And I don't have to keep re-specifying it over and over and over again. So now, we read in the data file, and we check to see that the data file read in correctly. And now we have to go to hauling, because hauling did a bunch of things in the first couple of pages of this paper, a bunch of things that you tried to probably ignore when you looked at this paper the first time, which are a bunch of equations. But one of the important equations that he has is y over x equals negative ABY plus TA. A is the instantaneous rate of discovery. B is the time to pick up a disk. So this is handling time. And T is the total time spent foraging, which in this case is 1 minute, which is nice because this becomes a pretty easy thing to work with, because this is 1. 1 times A is just A, so we basically kind of get rid of the T. So we basically have an equation that relates y divided by x to an equation where we know what the y-intercept is, and we know what the slope value is. A, B is the slope. And so if we want to know what B is, all we have to do is divide the slope by the y-intercept, and that will give us B. Well, why do we want to know A and B? Well, we want to know A and B because these fitted curves that are on these charts, on these graphs, are fitted to an equation that is y equals t times a times x divided by 1 plus a b x, where x is the density that we're foraging at, a is the same thing a was over here, and b is the same thing that b was over here. So we have to have a way of estimating what A and B are, and we do that by doing a regression of y over x regressed on x, where y is the number of disks that are captured, and x is the density of the disks. Okay, does this make sense?
I'm sorry.
What's what?
Go back.
I'm sorry. No. Y regressed on y, rather. Y is the number of disks captured, which we have shorthanded PCD, number of disks captured. X is the density, and Y is number of disks captured. So in the hauling paper, this is equation 5. This is this is equation 4. And all the equation 4 is doing for us is allowing us to fit a best fit line through the data points. Okay? So we're just dealing with hauling paper. So go back and get the hauling paper. The most important part of the hauling paper really is the first couple of pages where he goes through and explains what he's doing. He's going to regress y minus x against y. He's going to get this equation. He's going to use this equation to estimate what b is, because he knows what a is, because a is the y-intercept of this whole thing. And then he's going to use a and b to fit a best fit line that relates y to relates the number of disks captured to the density of disks that are present. So we're just doing some math. So the first thing that we have to do is we have to calculate y divided by x. We have to calculate the number of disks captured by the density. And so the way we do that in R is really good at doing simple math. So we're going to basically use the assignment operator here to basically say, I want to divide the number of disks captured by the density within this data file, and then I want you to store it in this data file under a new column. Right now, our data file has the name of the person, the density, the number of disks captured, and the handling time. This is basically saying, take this equation, this mathematical formula, and store it in a new column called ydivx in the FS data frame. And when we do that, it will give us a new column that is basically this divided by that. 1 divided by 4 is 0.25. 1 divided by 8 is 0.125, which is the decimal equivalent of 1/8. So what we've done is we've just used R to calculate y divided by x for every observation that we have in our data set. Now we need to run a regression between y divided by x and the number of disks we captured on that data frame. So we have y divided by x, and we have the number of disks that we found, and we're going to store that as a model. So this is just
Wait.
Yes.
Say it again.
Yep.
After the y divided by x part in a different manner.
So we found y divided by x, and we stored it in the data file.
Yes.
Now, in Holling's paper, he says, and I will read, when constants a and b are not directly measured, they can be calculated by transforming 4 into a straight line equation. Transforming this equation, which is a curve, into a straight line equation, where y divided by x is equal to negative a times b times y plus a. Y is the number of disks captured, divided by the density of disks. Y is the number of disks captured. So this is basically regressing y divided by x on y. And this is a linear model where a and b is the slope value, a is the y-intercept. So if you don't measure handling time directly, you can estimate it by doing some mathematical mumbo jumbo. So the first thing we have to do is we have to figure out what y divided by x is. Then we regress y divided by x on the number of disks that we captured, and it will return for us a line, and that line has this in it. Once we know what the slope value is, and we know what the y-intercept is, because the slope is made up of a times b, we can just divide a A times B divided by A, and that will return for us what B is. So we're just using mathematical equations to estimate what these parameters are so that we can then plug A and B into this equation and fit a curved line to data rather than a linear line to data. So we're just estimating parameters to allow us to do some curve fitting. So in order to do this, we have to run a regression of y divided by x on the number of disks that we captured. And that's what this is doing. When we get that, we basically have the y-intercept, 0.37239, and we have the slope value, which is negative and really tiny. And so because this is a negative in front of this, that's going to take that negative slope and change that to a positive. So we'll actually just use the absolute value of the slope. Now, one of the things that I discovered is that some of you have some pretty wicked outliers. So I invented a little plot to help us find outliers. It's a simple plot. You're not going to use it or anything else. You're just going to use it to identify outliers. But this is a plot that is going to graph on the x-axis the number of disks that you found, and on the y-axis it's going to plot y divided by x. And when we look at this, it basically shows that most of our data are pretty normal. There are a couple of outliers, but if there was only one out here, I would probably worry about it, but because there's a couple out here, and because there's a number of them out here, I'm not going to worry about it. The other reason I'm not going to worry about it is that when, oh yeah, so this is by person. So each of these lines represents a density. This is density 4, density 8, density 16, 36, 64, 128, and 256. And then each color is one of your data points. So I'm not going to worry about these things that look like outliers because it doesn't mess up the regression that comes out of this. So it doesn't mess up the parameterization of this equation and fitting the best fit line. So I'm going to leave it. The next one you're going to see is really wonky. So I'm going to save the summary data into an object called x. So I'm just basically saying, that model that I just ran, I want to save all the information in there. And the reason that I want to save all the information in there is because I want to not keep typing in numbers. So if we go and click on this, no, in there. If we go and click on this, I didn't mean to click on that. When we look at all of this, we can see that the coefficients are in here. So coefficients 0.32735, that's the y-intercept. Negative 0.00441, that's the slope. I have to plug those numbers into this equation so I can type them in over and over again, or I can just tell R to go and get it from this summary output. So that's why I save the summary output as x. So now what I'm going to do is I'm going to basically go and find, coefficient 2,1, which is the slope, and coefficient 1,1, which is the y-intercept. And I'm going to divide those because you want to divide the slope by the y-intercept to give you the value of b. And so that's this thing relating to these two numbers in the output from the regression model.
But didn't we, like, ourselves measure the time it took to pick up a disk?
Yes, we did, but if you measured time the way I measured time when I was sitting there measuring time, it's probably not terribly accurate.
So why do we even have to measure
Yeah,
time?
so why do we do
Why
it?
we use it?
Oh, we can actually look at, we're actually going to analyze the times that we recorded, and I'll show you that in a little while. So from that, we can get B. B is negative 0.0118537. And then what we can do is we can use this equation to fit a line of best fit through the data points. And we do that by erecting an equation that is basically that equation up there in R-speak. It's time is 1, so that doesn't even have to be entered in. It's a times x. A is the y-intercept, so that's that coefficient. X is density divided by 1 plus the y-intercept times the absolute value of beta and multiply that times density. And so what this will do is it will produce a new column in our data set called predicted that will then have the results of running this equation. And so now we have the original data, density, number captured, handling time, y divided by x, which we used so that we could ultimately get to predicted. And what you should see is that the predicted value matches kind of closely the observed value. Predicted matches fairly closely the observed value, predicted, observed, predicted, observed, predicted, observed. There's going to be some variation because Claire's data are not necessarily going to be exactly what the predicted data are, just like Logan's data aren't, just like Kennedy's data aren't. But we're not going to use this to look at the individual data points and how they fit the predicted line. We're going to look at the averages and see how they fit the predicted line. So now we need to go get those averages. So this next section here is just going to make a file where we're going to basically get the averages of the predicted values as they vary by density. Average of the number of disks collected by density, and it's going to give us a table that gives us the mean number of disks collected. It's going to give us the densities, how many observations do we have, all of us caught disks at one point or another, and then also gives us the confidence interval that we can use for plotting. But now we also need to get the predicted values in the same format. So we're going to do predicted values. The predicted values for densities 4, 8, 16, 32, 64, 128, and 256. These are the predicted values. They don't have any variation because the predicted value is the same for every individual for every density because it's just an equation.
The predicted value for number of disks?
Number of disks. So this is the predicted number of disks that you would expect to find if you were searching in an environment with 4 disks present.
Is this based on Claire's data or everybody's data?
Everybody's data. We just see the first 6 lines, and so we only see Claire's data.
Okay.
We could go and do this. Capital view, FS, and what that will do is it will give us a new tab that shows us everybody's data, but I don't usually need to look at that. But you can if you want to. Just use the view command. So now we want to take the predicted values that are in this data frame and we want to put the predicted values into the other data frame. So this is just basically saying, take this and put it in there, and then we'll see what that looks like. So when we take that and put it in there, we now have the average number of disks collected, and we have the predicted number of disks. And you can see that the predicted number is pretty close to the average. The predicted number is reasonably close to the average. The predicted value is very close to the average, et cetera, et cetera. Very close to the average there. So now we have everything we need to know to actually plot some graphs. So this is the first plot. We're going to basically take the data that are down here. We're going to plot density versus the number of disks captured. We're going to plot the confidence intervals. But we're also going to plot a smoothing function that will plot a line that relates density to the predicted values, which is what this does. And we're not going to use linear modeling because we know that it's not going to be a line, it's going to be a curved line. And so we're going to use what they call local weighted scatter plot smoothing. That's what LOES stands for. LOES stands for locally weighted scatter plot smoothing. It just takes data that aren't in a straight line, breaks those data up into smaller segments, plots regressions for each of those smaller segments, and then smooths the line that way. We're going to plot error bars. We're going to have two sets of points. One set of points are the raw data, and then the other set of point is the predicted data. We're going to put some labels on there, and we're going to use TH. Remember, TH is the common formatting block that I specified up there at the top. And we're going to store this as TYPFS, so type FS. What's the type FS? Type finger search sandpaper. So anytime we want to see this graph again, all we have to do is type in TYPEFS, and it will produce this graph, which becomes important later. And when we look at that graph, we have, voila, we have the observed data, which are the big dots here, and then we have the predicted line, which is just a plot of this line. We have a relatively good fit of the observed data to the expected data, and we see that this is a curve, which means that you make gains faster at low densities, and there comes a point where your rate of gain begins to slow down. It's not slowing down because you're depleting the number of disks, because somebody was always replacing the disk. It's slowing down because you're now spending a significant amount of time handling, because you're spending a significant amount of time handling a significantly more number of disks. At this point, you're handling 35, 40 some odd disks. Each disk that you handle has a little bit of handling time associated with it. And so you can't continue just getting more and more and more disks, because each disk requires some handling. So this isn't a diminishing returns curve. Don't confuse that. It's not a diminishing returns curve in the sense that we talked about it in class with the dung flies. It looks like a diminishing returns curve, but it's not due to the fact that you're filling up a female with sperm. It's not due to something like displacement rate. It's just the physical limit of every disk requires a certain amount of handling time. The more disks you handle in a minute, the less time you have for doing other things. Each one of these trials is 1 minute long. If you handle 30 disks, each disk takes a half a second to handle. You basically spend 15 seconds out of the 60 seconds handling disks. And so you're really only searching for 45 seconds. That's why the number of disks that you capture, the rate of gain of that is slowing down, is because of a handling time constraint. Okay, does that make sense? This plotted the means. We could just as easily plot the raw data. So rather than plotting the means, I'm actually just going back to the original data file and plotting the actual data points. And so on you didn't get what? What? Stop me if I need to go back.
No, you're good. You're good.
So on the last page is the data points version of what is on the first page. I don't care which set of graphs that you use whichever ones you feel more comfortable with. These give you some idea of where the variation is coming from. This one basically just puts all of that variation into a confidence interval.
So-
Yeah.
What do you call this kind of graph? 'Cause you
This is
said
a functional response graph.
functional response. So
Sure.
it'd be like functional response curve.
Yeah, so if I was writing a figure caption to this, I actually would call it, I wouldn't call it that. So remember that all captions have a descriptive title. So the correct format for a caption is figure 1, title, explanation. Figure 1. That's the title. That's what it is. It's a plot showing you the relationship between the number of disks captured and disk density. Now the explanation is answering the question of what does this mean? Well, it's showing you that as disk density increases, the number of disks increases, but it increases at a decreasing rate. What is the nature of that decreasing rate? It's a functional, it's a handling time constraint. Because as you get more disks on the table, you spend more time handling because you're capturing more disks, and because of that you have less time for searching, and so that's what's slowing down your rate of gain. Yeah.
So if we made that the title, we would have to make that the title of all of our figures, wouldn't we?
So now all of your titles will be different, and they are actually now more descriptive, aren't they? Then you say, what does it mean? So yeah.
And, okay, so the bars on the graph on each dot are 95% confidence?
Those are 95% confidence intervals because that's how I calculated them.
And the back page doesn't have those?
No, it just plots the raw data. So you can either present your data as means and 95% confidence intervals, or you can actually show people the raw data. It doesn't really matter for this exercise. And we're not doing any sort of statistical tests on these things. We're not testing to see if the slope of this line is significantly different from 0. These are simply descriptions. And the thing that you want to talk about is when you look at all of them on the page, what do you notice about the y-axes on all these? What's that, Coach? They're all the same. I've scaled the y-axis. So what I had to do is I had to run all of these. I had to figure out which one had the highest number of disks, which was always the type 1 no handling time. And I had to scale each figure so that each figure has the same scale, so that you can look at this one easily and see that no handling time results in more disks captured than when you have any form of handling time constraint.
Wait a second. Are all of, so is this page, and this page all different versions of the same thing?
No, this page is number of disks captured. This is handling time. What they were asking about, why did we measure handling time if we weren't ever going to use it? This is handling time. This is just a raw data version of this. You see that they are the same.
But all of our data didn't look so like, I mean, when you had it over here, it looked less beautifully lined up than this.
What do you mean?
Like all of our data was like in weird, colorful rays, and this looks like perfectly lined.
The color-coded thing you had on the screen, like 5 minutes
We
ago.
were talking about outliers.
That's just to find outliers.
Okay.
This is the plot that we're looking at. And the reason that it looks different is because these plots are squarer than, they're a different dimension. Blow them up to the point that they, so the other thing is that we're not looking at this plot, we're looking at finger sandpaper. This is finger sandpaper. They're in a different order.
I'm simply asking you, how can all of our dots be in such a beautifully perfect straight line on this back page?
Because it's all 256 disks. The x-axis is number of disks on
Oh,
the
I see,
table.
I see.
Yeah. Always pay attention to what your axes are.
So will we have to change the y-axis thing, because that's different than we have.
Okay, so this is not different, but this is different because these are more variable. The raw data are more variable than the 95% confidence interval is. So I had to change the y-axis on the back page because for this one we have like 110 disks. Caleb.
actually found 110 discs.
Yeah, something like that.
I'm gonna call BS.
So these two are just
No.
different representations of the same data, but on this page, they're all scaled at the same y-axis. On this page, they're all scaled at the same axis on the page, but this axis is different from this axis because this is raw data and this is 95% confidence intervals. I don't care which set of figures you use, just make it consistent across all of them.
Would you recommend doing these each as individual figures or like putting them together?
No, I would put them all together. So I would, so figure one, actually for me, if I was doing this, I would have one panel that shows disk density data, relationship between number of disks captured and disk density.
I'm gonna do A, B, C. This brings up another question. Is there a rule for when you use C and K in discs?
No, it's, both are appropriate.
I've been wondering that for a long time, but it just seems like.
So you could certainly make this the title of your figure caption, or you could also just do this. So actually, I would probably do this if I was doing this,
Okay.
because that first title was just too many pain in the ass to write and read. There are lots of correct ways of doing a figure caption. Use the one that speaks to you. Once again, as long as it has a particular form. I've chosen a form here that has a shorter title so that I can spend time doing the explanation. And the explanation in this is basically dividing it up into panels. You could certainly do figure one, figure two, figure three, figure four, figure five, figure six, and divide them up and have each figure a separate standalone thing. Why do I like having them all together?
Because then you can compare them in one spot.
It's really easy to compare them in one spot and see what the differences are. And they're not going to be statistically tested differences. They're going to be differences that you eyeball. There are no statistical tests to look at these. I mean, there are, but it's way beyond what we have the time to do in this
So-
class.
Okay, so when we're discussing how we generate, you want us to discuss the process by which we generated these graphs and the methods.
Yeah, and the method for doing that is in the introduction of Holling's paper.
Okay.
It's all right here.
But we don't have to put it in our introduction. You want us to put it in the methods.
It would be in methods, yeah.
All those equations?
Sure, yeah, because it makes sense that, where on earth did you get this line? Not an appropriate way of thinking about it. So take a little bit of time and go back and reread the first couple of pages of Holling's paper. When I first started teaching this, I had to read the first couple of pages of Holling's paper a number of times before I could sit down and write the first R script that actually produced graphs that look like Holling's. Because I had to figure out, well, what the hell does he mean when he says regress y over x over on y? How does that help you figure out what the instantaneous rate of capture is and what the handling time is? How does that then translate into being able to draw the predicted lines? I had to work through that myself for a little while before I could sit down and code something to do it on the computer. Yeah.
What is instantaneous rate of capture? What does that mean?
That's basically over the time period that you are searching, essentially, what's the rate at which you're finding and capturing prey. What's weird about it is that it doesn't really change much across densities, as it turns out. When you look at when you look at table 1, sorry, instantaneous rate of discovery rather. Instantaneous rate of discovery, when you look down this thing, doesn't really change that much for a particular search method, finger sampling or whatever. It will change from one search method to another, but it doesn't change much with density, nor does handling time typically change much with density, although it changes a little bit. So, and we'll see these are all estimated from this figure, from this equation, but oh no, these are actually observed data from actually timing it. But you could easily estimate those things from this thing. You're going to see in our data in just a minute. Let's do that. Let's get handling time. So in handling time, I omit any handling times where people didn't find any disks. So I've coded that in the original data file. If we go up to, well, it's not going to do it for this one. I'll do it for the next one. Anytime you didn't find a disk, a handling time is 0 because you didn't handle anything. So that's not really a realistic handling time. It's just that you failed to find any prey. So I've gotten rid of all of the zeros that correspond to 0 prey captured. That's what this NA omit is about. And we can look at handling times. We can produce once again, a data file. So 3 of you didn't catch any disks at a density of 4, and so there's only 6 observations rather than 9, which is what there should be, and that's because for handling time, 3 of you didn't experience handling because you didn't capture any disks. Once again, this is the average handling time, and you can actually see for your data, the handling time goes down. When you start with single disks, it takes you longer. At low densities, when you start at low densities, it takes you longer to handle the prey than when you have higher densities. And there's actually probably a good reason for that. He did not experience this with his students, and it has everything to do with how his experiment was run versus how your experiment was run. Not only that, your handling times are generally a little longer, strikingly enough. Is that right? Yeah, considerably longer. So this is one of the things that you want to think about when you think about how he did things versus how you're doing things. And then we can create a plot of this. We're using low S smoothing as well. And what you see is that at low densities, handling times are relatively high, but then after you get to higher densities, handling time goes down. You have to think about why would handling time be related to density, such that the more disks you come into contact with, the handling time per disk goes down. So that does the finger sandpaper. I just collapsed that. We can now look at pencil sandpaper. We do the same thing. It's the same set of steps, just over and over and over again. We get the data in, we look at it to make sure that it came up. This is a not available because there is no handling time associated with catching no disks. So it's going to omit those when it does the handling time calculations. We need to estimate A and B. We do it the same way, except now we're using pencil sandpaper rather than finger sandpaper data. So it's just the number of disks captured divided by the density. Same set of steps. We're going to do a diagnostic plot to look for outliers. And then you have to just ask yourself, what was Logan on? That is a pretty severe outlier compared to all the rest of the data. For some reason, he's
Top of the food chain.
He's at the top of the food chain. So what we do next is we're going to look at this, and once again, we see that everybody else is kind of normal, and then Logan has this really extreme outlier. I only detected this because when I did the fitted line didn't fit the data at all, and it's because that one point skewed the regression of y divided by x regressed against y. It skewed the slope of that, which then totally messed up the predicted line. And so what I had to do was I had to get rid of Logan. So I just deleted, this basically just says drop levels, drop any observation that has a y divided by x of greater than 1. That got rid of that outlier. You see Logan, that one that was way up here at over 1 is now gone, and we can proceed. We just go through the same calculations for fitting the line. Our predicted values are now there. We create summaries of all this so that we can get it all into a common data frame where the density is what is being on the x-axis, the number of disks captured is on the y-axis, and we will also plot the predicted values. Once again, you see that the predicted values are fairly close to the observed values, which is, once again, what you would hope if you're fitting a line that is described by the data. And so then we make this figure, and once again, we see that very close fit of the predicted line to the data, but it's different than the other one. So this is, the first one was finger sandpaper, the second one is pencil sandpaper. You see that you get many fewer disks when you're searching with a pencil than when you're searching with a finger. Why? That's a difference in detection probability. You're listening for a sound difference, you're not feeling a tactile difference with your finger. Because you have a difference in detection probability, you sometimes set your pencil down on a disk that is a disk, but you don't recognize that it's a disk, so you just keep searching. So as you go through this, as you get each new result, ask yourself, why does this figure differ from this figure? That's a search detection issue. But because also you have a pencil in your hand, you might also be somewhat hindered by handling time constraints here. How can we see if we are hindered by handling time constraints? Let's generate the next figure, which is just the raw data. Let's go look at handling time, which is the next plot. Well, now we can look at handling time, and we can see that handling times are slightly higher at the beginning. Not only that, they stay higher over the course of it. So the difference between these two figures here is both a detection probability issue as well as a handling time issue. It's not just one thing leading to the difference in those two curves, which is why we're looking at the handling time data that we actually collected.
So there's a handling time issue in all of these 4 bottom ones.
There's a handling time issue in all of them except for the one that has no handling time.
Well, that one doesn't look that much different than clumped prey.
It's the difference between an average number of disks of 42 or something like that, which you can go and find out when you look at the table. So under no handling time, what was the no handling time data? Let's go back up to no handling time. Oh, we haven't done it yet. It's the difference between, for clumped prey, an average of like 42 or 44 or something like that, close to 50, versus about 65, 68, something like that. So is it better to eat 30 prey versus 68? I don't think so.
Yeah, but
So if you can avoid handling time, if you have a method of capturing prey that doesn't have any handling time, your rate of energy gain, your rate of capture goes way up at the highest densities. And it's also higher at 128 density, it's higher. So if you look at this dot versus this dot versus that dot, this dot versus that dot, this dot versus that dot, or this dot versus that one versus that one, freeing yourself up for handling time significantly increases your ability to capture prey.
right, but how am I supposed to look at this line that's basically
Oh.
zero slope and think of handling time as an issue with clumped prey? Which it wouldn't be because we were, when
So-
we did the clumped prey, we weren't putting the discs in the bag either, were we?
Yeah, you were. You should have been. Clumped prey? Yeah, you should have been putting discs in the bag for all of them except for the no handling type, the type 1. So when you run these, here's why you need to run the scripts themselves. When you get down here to handling time, you're going to produce a figure, but before you produce a figure, you're going to produce actual numbers. So here at 256, so this is for finger search. Finger search for densities of 4, your handling time is 3.03. For 128, 256. This is for finger search, 3.03, 2822, 0.6 something, 644. For pencil search, let's go down to pencil search. I'm going to double click here and collapse that. So now we're going to look at pencil sandpaper. Go to the bottom of that. When we produce this handling time graph, before we produce the graph, we have to produce the data that are in it. And what we see is that handling time for pencil search was 2.86 handling time at low density, so it was lower, but it's 1.45, and 1.0 at the highest end. So this is handling time differences between these two things. So even though you look at the lines and they look like they're pretty similar, it's visible to me that one is higher than the other, and it's higher than the other by this much. Okay, so
Yeah, but like I can't have a valid discussion about that in my lab report unless I include those numbers, which seems like it would be a lot more trouble than it's worth. Unless I just talk about how the line is qualitatively higher than the other.
Like, are we just supposed to mention that they?
yeah,
Like these-
once again, we're not doing statistical tests to see if this number is statistically different from that number. You really are making qualitative distinctions here. And so one of the ways that you could do that is you could draw horizontal lines across from one graph to another if you wanted to. The way I would do it is I would actually just refer to numbers in the text. Because look at both of these, especially the no handling time one. Those are all down really close to 0. And if you generated these data for that, which you will, it would show you that those are all down really close to 0. Which also makes me wonder, did you guys do your own bagging with the clump parade?
Well, you worked with us, so we.
I thought you did. Hmm?
Yeah.
Yeah, okay. That does look a little weird to me, but every semester the class is different. For example, I've never had to go through and filter outliers until your class. And that actually caused me quite a bit of programming vexation and how to find which one was the outlier, how to identify it, and then filtering it out was pretty easy, but how to identify it, I had to spend some time on.
So how long did it take you to do all this? So, why do you expect us to do it?
I don't expect you to do it.
Oh,
You didn't do this. You're using a script that has been written for you to reproduce results so that you can actually look at tables like this. No, I'm not asking you to write an 700 and some odd line script. I've written the script for you. I put in the time to write the script for you. All you have to do is run the script, which should run perfectly well, assuming that you have the script and your data all in the same place. But for me to just give you the output, you don't ever get the opportunity to go and see, okay, to answer Alexis's question, which is, how can we tell if those things really are different? Well, it's hard to eyeball it on the graph, partly because the graph for this is scaled in such a way that it includes this really wide variation here. If we made the scale wider and got rid of this variation here, just cut it off essentially, you would be able to see those differences easier. In the same way that you might be able to see differences easier if we had less of a wide scale on these things. But you can't make comparisons if you keep changing the scale of the y-axis. So it's easier to make comparisons for the disk data, especially if you keep the scale all the same. It's a little harder with handling time because handling times are so short anyway, because you're just picking up a disk and throwing it in a bag. It takes you less than a second to do that on average. So if there's any variation around that, that makes the scale much bigger, so it makes it harder to see those differences, even though those differences do exist. But you go and actually look at the data outputs to see those differences. Yeah.
So when we're running this on our own, do we just click Command Enter, Enter, Enter to go all the way through and run and see?
Yeah.
Or do we have to like know which one to do?
No, no. So you can start at the top. So when you get here, my advice would be to leave it all collapsed. Open up one type at a time. Click on the arrow. Open up Finger Sandpaper. Run Finger Sandpaper. When you get to the bottom of Finger Sandpaper, you'll get to the last figure that will look something like that. It will always be a handling time one, because these scripts are exactly the same. The only thing that changes is the data. When you get to the finger handling time one, click over here in the gray bar, collapse that one, and then expand the other one, so that you can keep things straight in your head what you're looking at as you go. I always, when I'm running scripts, I always have a piece of paper next to me, because sometimes it's nice to note some of the details as you go through there, so that you can then look at some numbers as you see your graphs being generated. First question, are the numbers on the graph actually the numbers that you saw in the data frames that went into making the graph? And the other thing is, you have these questions eventually, like Alexis has. How can you tell that those handling times are different when the lines look so similar? They look so similar because they're all really close to 0, but they're not similar when you actually start to look at the numbers. And so I always have a sheaf of loose leaf papers. This is going to be offensive to you. A sheaf of loose leaf papers where I'm jotting down notes. You can have your iPad. You can have your iPad where you're jotting down notes about the script that you're running. I would not do the thing where you basically highlight the entire script, plus command return, and then just wait for it to spool out. Because if there's an error, you're not going to see it. It's going to be throwing graphs at you, madcap, graph a minute. And so I would break it up into sections. Do finger sandpaper, do pencil sandpaper, do finger transparency, do pencil transparency, and pay attention to the script as you go through it. That's why I generally go through scripts line by line. Even scripts that I know should work and that I wrote myself, I go through them line by line just to keep my thinking straight about them as I'm going through them. The same way that I'm going through them now. I could just highlight everything in finger transparency and it would just blip it all out at you. But you would miss paying attention to these. And I've been moving through these pretty quickly, but looking at that versus that is informative. So you can tell that this is pencil search because the pencil search data frame is what's being used. This is pencil sandpaper, this is finger sandpaper. Finger sandpaper, 3111000, 2212111. Paying attention to these numbers actually is informative. So work through the script slowly, deliberately, take notes on the script, on the outputs that the script is producing for you, because you'll want to talk about these things in your paper. So no, I did not ask you to do this. I did this. All you have to do is take something that I've created for you and be capable of using it. I would never expect you to create this.
Imagine, like, I feel like your value as a human being, if you can use R, is just like incrementally increased. Like,
You can certainly get a pretty good job if you can use R. It's not really, it just gives you a set of skills that some other people might not have. And quite frankly, it can be really infuriating. I was last night, so I worked on this some last week. I worked on it a good chunk of the day yesterday when I was free. when I was getting predicted lines that didn't match the observed data at all, I knew something was wrong. It took me a while to figure out what it was that was wrong. And then when I figured out a way of graphically identifying whether or not I had outliers, that made life a lot easier. So we've done pencil sandpaper, we can do finger sandpaper, same process. We get the data file in, we do the regression of y divided by x. Well, yeah, y divided by x. We get that added to our data frame. We then do a regression of that. We plot. So after I discovered the first outlier, I just made doing these outlier plots a part of every aspect of the script so that I could go and look at them. This is still pretty high, but it's not really that much higher than the next nearest point. These are also pretty high, but they're not that much higher than the next nearest point. So I just kind of left them in there and left them alone. We get the value of B. We use that, A and B, to give us the predicted values. We now have the density, the number of disks captured, the handling time, and the predicted values. We're going to use these values to give us the data on the actual number of disks captured. We use it to give us the predicted number of disks captured. Then we combine those into the same data frame. So we now have the number of disks captured. We have the predicted values. Here, once again, you see reasonably close, although not perfect, correspondence. And that is what we're going to use to generate the graph. The graph looks like this, which once again should look like finger transparency down here in the bottom. You can also get the graph that shows you all of the data illustrated if you want to do that instead. Except there's a problem with that. I missed this one. And then it also gives you a handling time. So once again, look at the handling time. These handling times are slightly higher.
Is that what's supposed to be?
What's that? Let me see.
No, don't worry.
Let me see.
Everything's just like listing out.
You're installing packages,
Okay.
is what it looks like to me.
Wait a minute.
Yeah, those are all warning messages that are just for your information messages, not something's catastrophically wrong. So look at the handling times once again. You see that these handling times are higher than the sandpaper, than the finger sandpaper search, but lower than the pencil sandpaper search. Why are handling times higher for the transparency disks? They're harder to pick up off the table. And because they were a little harder to pick up off the table, the handling times are a little higher. They're somewhere between picking sandpaper discs up with your fingers and picking sandpaper discs up with a pencil in your hand. And so once again, there's a difference in handling time constraints. That is visible when you look at the numbers, that may not be very visible when you look at the line. So as you work through the script, don't just use the script to generate a bunch of graphs, actually pay attention to the data output. The data output are always going to be in line within CI plot. And the CI plot will be followed by the data file. If it's just followed by the data file, that's disk data. If it's followed by the data file and TH, those are handling time. Okay, so this is CI plot, finger transparency, handling time. That's what those data are about. So I've tried to make the script as clear as I can so that you're not befuddled by it as you go through it.
But that's not what that showed, right?
No, because I stopped before I got to the end. So we generated that data frame right there, which is the same data frame as that, so we could then use that to make this plot. Okay, yeah. So then we can go to pencil transparency. Same song, fourth verse. Read in the data. We have to find A and B. We have to identify outliers. oh my gosh, there's an outlier, and that looks like that is Caleb. The next nearest person has like 30, and you're here at like 62. How did you manage to do that?
That's social learning.
Is it a 62, or did you accidentally transpose 26? Okay. What were you doing? What were you on? What drug were you taking that day? What? So this is, you put the pencil down?
No.
Yeah.
As if I touched the table.
Yeah.
Kind of slide around.
Okay, so you used a different search strategy than maybe other people did. Anyway, we got rid of you. This is the line that gets rid of you, so that when we look at it again, it's more normalish looking. The only reason I'm getting rid of these outliers is because it changes this equation. It changes this equation such that the line that is produced from the equation, this is the equation, isn't it? Oh, AB. No, it shouldn't be AB. ABX. It changes the predicted line such that the predicted line didn't match the data at all. And one really extreme outlier is enough to change the parameters of this, that the predicted line doesn't match the data very well. So that's the only reason that I'm screening the data. So we generate the predicted values, we get the raw data, we combine the predicted values into the other data, and that gives us number of disks captured, the predicted values, and once again, we can generate figures from this. Now we have pencil transparency. Pencil transparency is the lowest. Of all of these plots, the worst way to forage is forage for transparency disks using a pencil as your primary search tool. Because it affects what? It affects handling time because you have a pencil. It affects detection probability, and it affects handling time because you have a pencil, and also handling time because it's harder to pick those up than it is to sandpaper disks. So you have two kinds of things adding to handling time, and the pencil and the fact that you're trying to pick up transparencies, and you also have a slower rate of gain because it's harder to detect them. So one of the things that we should see when we look at this is when we look at handling time, we should see high handling times.
What are the units on handling time?
Seconds. All of this is recorded in seconds, because that's what you were recording on your stopwatches, yeah.
Do we use the Hawley equations to generate the predicted value?
Yes, that's how we're generating the predicted values. That's why we're doing all of that. Y over X equals minus ABY plus A. We regress this on Y so that we can get the value of AB, which is the slope, and the value of A, which is the y-intercept. Because AB and A both have A in them, we can divide AB by A. A cancels out, giving us the value of B. So now we know what the value of A is to put into this, and what the value of B is to put into this. And then this is not a line, this is a curve. And that's the curve, in theory, of best fit of the predicted line to the raw data.
So why do these handling time graphs have like little dips in them?
Because this is a low S. So what low S, what locally weighted scatter plot smoothing does is it's a statistical technique that if you go to graduate school and take a graduate level statistics class, you will be exposed to, which once again, Kennedy, is why I'm not asking you to actually build a script to do this. But what low S does is if you have data that are nonlinear in nature, as X increases, Y goes kind of all over the place. What low S does is it basically looks for subsets of the data that have significant regressions, and so it would break this data up into this section, break it up into this section, break it up into this section. It would plot a regression line through that section of the data, plot a different regression line through that section of the data, then it plots a regression line through that section of the data because these are areas of the data that have clear trends associated with them. And then what it does is at these intersections, it essentially smooths this off. So it's a smoothing function, but it arrives at that smoothing function by subsetting the data into little sections across X where Y is covariant with X, either positively or negatively, and then stitches those different regressions together. So that's why it's called locally weighted, because it's weighted by how you're calculating the predicted value of Y is weighted by what the relationship between X and Y is, not over the whole thing, which would have a regression line that's a slope of 0, the way I've drawn it here. You're weighting it by what's happening locally. How does X vary with Y over short spans of X? Then it calculates a bunch of little regressions. And so that's why it's doing that little wiggly thing at the beginning. On
So it's not like necessarily a trend in handling time, it's just like a consequence of the method used to generate graph?
So the shape of the line is a consequence of the method used to generate the predicted line. But that's driven ultimately by the data. So let's look at what it is for this. So here you have handling time varies somewhat, but these are all not significantly different from one another. But then after you get beyond 4, 8, 16, once you get beyond 32, it goes down. But because this was trending upward, low S had it trending upward. Then because this trends downward, it has it trending downward. And because the next point is, so this is 8, 16, 32, 64. Since the next point is 128, there's a lot of distance here. It continues that trend down until it gets the next local point that would then pull it back up. So when we're doing this with individual single points, like we're doing on the handling time data, the distance between the points is actually affecting this.
So for this graph,
this continues trending down until it gets some information that says it needs to come back up.
right, but why wouldn't I just assume that all 4 of the last points on this graph are just the same, like essentially the same?
They are.
regardless?
They are essentially the same. And that's especially obvious when you look at the data. 1.33, 1.34, 1.22, 1.161. Slightly smaller, but not very much smaller.
So the trend here is that as prey density increases, handling time decreases?
Slightly. Slightly. Because it started out actually pretty fast anyway. I mean, reasonably fast compared to, it didn't start out at 3.
Yeah, I guess like, if you look at the confidence intervals, none of those points are like really that different.
No,
So-
no. They're all down around 1.3 to 1.5.
So then what do I get out of this, like having this?
You get the fact that this is not, well now I've erased it, this is not 0.6.
So when we talk about this,
It's not 0.6, which is what it was for some of the other ones.
So maybe having the handling time and the number graphs would be a smarter idea next to each other?
Sure, you could do that. Or just make a set of tables that has the handling time data for all the different things if you find that useful. So I think the important thing is not the shape of the line as much as it is where the line is located vertically on the y-axis.
so when we talk about these things in our lab report, do you want us to be using numbers, or are you okay if we just say the handling time for pencil and transparency as prey density increases is slightly more than what it is when you are using?
That's fine, as long as that statement is correct.
Okay.
Yeah.
So you don't care if we give you numbers to prove that?
I have an R script, I can always go and look at those numbers. And before I sit down to read your lab reports, I'm going to write a results section that basically has what all the results are, so I don't have to keep going back and rewriting running the R script, I'm gonna say, when I look at handling time, which one of these plots have the shortest handling times? Well, it's this one. If I'm comparing finger searches versus pencil searches, how does handling time change over those? So before you sit down and before you hand in your papers, I will have gone through the data and said, how does handling time vary over these things, so that I'll have on a page next to me what those numbers are, so you can either refer to the numbers and then I'll look at my numbers and make sure that they're all the same, or you'll make a qualitative statement like that and I'll look at my numbers and say, okay, that qualitative statement is correct. So in order for me to grade these things effectively, I have to understand the data at least as well as you understand the data.
So, we have to not only, I mean, we have to compare finger to pencil, but also finger to finger to, with the sandpaper and transparent, like we
Sure.
have to compare it all.
Yeah. I wouldn't think about it that way. I would think about what the main things are that I've now erased. What are the main things that determine functional responses, what the shape of the functional response is? One of them are handling time constraints. One of the things that affects them is detection probability.
But there are two things that go under handling time, yeah.
Yes, okay, so, and the third one of these, what did I say the third one of these is?
Spatial.
Oh, yeah, spatial distribution. So if I was writing an introduction about functional responses,
Yeah.
I would basically define what a functional response is, and then I would talk about what a type 1, a type 2, and a type 3 functional response are, and I would talk about how they differ from one another in terms of, are they different because of handling time, are they different because of detection probability, or are they different because of spatial distribution? Then that sets me up for talking about the methods where we had different methods to basically jack with each of these things in somewhat different ways. And so I wouldn't necessarily write my methods in the order in which we did things. I would maybe rearrange that order so that I basically talk about what are the methods that we use to basically manipulate handling time. Well, we did two things. We did that in terms of finger versus pencil, which affected handling time, versus none, which is the type 1 response. And what were the experiments that we did that basically allowed us to draw these distinctions? Then what were the experiments that allowed us to draw the distinction in detection time? That's the difference between finger search versus pencil search, but also the difference between sandpaper discs and transparency discs. Both of those deal with detection probability, and then the only thing that dealt with spatial distribution is finger no handling time, which is exactly like the clumped prey data, except that, finger search, finger sandpaper versus finger sandpaper clumped. That's the comparison that you have there. And so don't think of it as what graphs do I need to be thinking about. Think of it as what are the fundamental things that affect functional responses. Then what are the experiments that inform them about those
So I
things?
just like introduction 1, 2, 3, methods 1, 2, 3, results 1, 2, 3.
Yeah, sure. That's easy to understand, isn't it? Why make life hard on your reader rather than difficult on your reader? Because your reader is going to...
It's more difficult for you.
What's that? Oh, yeah. No, I have to read these, and so if you can organize them in a logical way, then that's better for all of us. So back to...
It's a nice number of conversations about this I can have.
Yeah, that's all I'm trying to get is that.
I'm just, I feel like I have enough to think about now.
Okay, before we go, so this is pencil transparency. And we'll get to finger transparency real quick. So back to your question. This is pencil transparency, handling times. This is finger transparency, handling times. What do you notice about the actual numbers? You're both handling transparency discs. What happens when you stick a pencil in your hand?
Which is the
Takes
pencil?
longer.
Pencil transparency, finger transparency. Pencil in your hand takes longer. So 0.7, 1.1. Finger transparency, pencil transparency. So whether you write about this in a qualitative way or whether you write about it and refer to actual numbers in tables, it doesn't matter to me. I'm going to have all this shit printed out in front of me so that when you make a statement, I will go to those numbers and I will say, is that statement true and accurate? And so I don't care if it's a qualitative statement or if it's a quantitative statement. I mean, all those qualitative statements are quantitative in a sense in that you're saying something is more than something else. But once again, I want you to be talking about handling time as it varies across these different experiments and what that tells you about the importance of type of prey that you're eating. So don't think about this as discs of sandpaper, discs of transparency. Think of it as two different prey types that differ in their handling time. Imagine that you are eating so in the Pacific Northwest, where Tareca newts occur, there are these big salamanders called Dicamptodon. They're big, they're beefy. If you can down a Dicamptodon as a snake, you might not have to eat for the next 2 months. There's so much energy in them. Now, one of the problems is they're big, but what they are not is they're not toxic. Now, if handling a Tareca, which is much more common than Dicamptodon, I've collected lots of Tareca in my life and I've never even seen a Dicamptodon, and I've looked for them. So you have one prey item that is toxic, you have another prey item that is not toxic but rare, so you end up eating the toxic salamander, but because it's toxic, it knocks you out sometimes. The handling time associated with that prey is much greater than if you were just eating Dicamptodon, which you can eat because they're just not very common. So don't think of sandpaper discs and transparency discs as two different disc types. Think of them as two different prey types. If those prey types require more handling, what does that do to your ability to capture and eat them? Well, the more handling and time associated with them, the fewer you capture in a minute time. So all of these trials were 1 minute long. The question is, how much prey do you harvest during that minute? How does the detectability of the prey influence how many you capture? How does the handling time associated with that prey affect how many you capture, et cetera, et cetera? Don't think of these things as sandpaper discs. Think of them as different types of prey with different challenges associated with them. Otherwise, I would just send you out into the field and have you catch squirrels or something. What's that? It would be so much fun, except you would never catch squirrels because squirrels are so much better than you. This is something that we can do that gets at some of the ideas, fundamental ideas, handling time, detection probability, spatial distribution, that keeps you from going out and spending hours and hours and hours trying to catch prey that you're never going to catch.
Okay.
Does that help at all?
It's just like there's a lot, I'm gonna have to personally process it.
Which is why there's a long timeline for you to get this done. At the end, so we're running out of time. So I'm going to do something that I advocate that you never do, which is I'm going to
I just wish our art looked nicer.
I'm going to highlight this whole thing except the end here.
It's so ugly, I have no idea.
And what I'm going to do when I press this is it's going to run everything.
Just click Command Enter.
I highlighted the whole damn thing and I clicked Command Enter because we haven't generated all the drafts and I want to show you how I produced this.
That page?
Each of these pages, this page, that page, that page. So here comes the figures. Hopefully it will produce all of them. take long. Do you want me to do that?
I guess I could do it in your office.
Yeah, it's not hard to do. I can easily do that.
That way I just don't have to like say it awkwardly in my caption.
It's always a good idea to put units in, well, the disk density, I mean, that is the units.
Well, yeah.
It's number of disks. Number of disks captured is number of disks captured. So
I
the
just
only ones I
meant-
would have to
yeah,
do is
for
on the
the
handling
same
times.
time.
Yeah, that's fine.
Don't say that.
So disgusting. I feel so bad for you.
Yeah, that's it.
Your life is. Biofuel Lab is like just absolute garbage. Biofuel Lab, like, I never knew, I was like, wow, this took me 1 hour to determine what I was supposed to do and I did it wrong. Like,
Like, so you have,
it's.
If you want to know, like, how to figure out how to.
Who's in your group?
So you can get like these.
Yeah. yeah, we'll just like.
I was with Chris and Haley, it was horrible.
Kayla and
That was awesome.
What?
I was with Chris and Haley, and they were arguing the entire semester. Super.
and Haley.
Well,
Oh.
so it was just a real solid. I just eventually was like, you guys can leave, I'll do this. And, you know, I'll just do my own group.
Okay.
As always, and she would know what she was doing, so she would be trying to correct Chris, and then I'd be like, no.
My favorite time during micro was with Bobby.
What does it have a title on it?
She also roasts.
I remember it so like.
Okay. So down here at the bottom is a package called Multiplot, or a command called Multiplot. What a multiplot does is it'll put a lot of plots together. And it basically has two arguments. It has an argument of what are the plots that you want to plot, and how many columns do you want to put them in. When it plots them down the column and then down the next column. And so I've done it so I have all 6 plots on the same page, but you could do 4 plots on a page or whatever. Just alter which plots they are, but realize that it's going to arrange them. If you have 6, it's going to do A, B, C, D, E, F. If you have 4, it's going to be A, B, C, D. It's going to go down and then go to the next column.
Will it resize them?
It will resize them automatically, yep.
Can you resize them after you create this page? So if
Yeah.
we wanted to fit 6 plots and the figure caption on there?
No, you would have to. So here's the other thing. So let me generate these.
Well, I think it is probably better if you did A, B, C, D, E, F, like if it resized it to where you long ways, then you have more for caption.
Plot rendering is really slow on my computer, and my computer's about to die. So we might not.
I did an entire update and only brought it down to 63%.
So what I would do is, when you get a plot done, and I've done this with these guys, go to the Export tab here. And on the Export tab, actually stop. So if I want to save this as a plot,
Oh.
go to the Export tab, save it as a PDF.
Error.
Export it to a PDF, give it a descriptive name, and if you save it as a PDF, when you open it up as a PDF, just take a snapshot of it, and then that'll then just embed that in your Word file and then put a caption underneath.
Can't we just take a screenshot of it right there?
It won't give you nearly the resolution of saving it as a PDF will. So you could take a screenshot, but if you change the size, it's gonna get all pixely.
Paul, do you have somebody go to your office right now?
What?
There's someone at your office right now.
I don't think so.
Can I come?
Yep.
Two quick questions. One,
First, I
Wait.
have to run this.
Before you leave, if you have problems with this, come see me in my office. I can walk you through this. If you're having trouble getting R up and running on your computer, I can walk you through that. You're gonna be using the computers next door. A lot of those computers are being used by my applied stats class, so a lot of these packages that you're gonna be looking for are already installed on those computers. So you're in some ways better off than some other people.
I got you.
Oh, yeah.
You managed to.
How's it been?
I just did a bunch of things and I heard
That's awful. Brother, we need to, how do you go, your next grad school? Better we can. I didn't really start using my iPad until this year because I was trying to train myself to take notes on it, but I can't figure out how to get the live to update on there, so I'm
Honestly, I don't have any storage. If for some reason it breaks, I'm effed.
like, what if, I always think about that when I'm taking notes on GoodNotes. I'm like, what if this just crashes? I lose my whole
There's an automatic backup on the new one, on the GoodNotes 5. It helps.
Shut up, Jack. Oh, I'm gonna take a high resolution image. Claire, what is that laptop?
It's my brother's. Bulky.
Jalen, you're working with the boys, right?
Yeah.
Claire, I think the smartest thing for you and I to do would be to divide into the other groups because like.
That would be like 4 and 4.
That's what Paul suggested.
4 and 4. I
The
used to
lab
use it
groups.
for
4 and 4.
I did not suggest that. This
I
works
thought you
never.
said two groups of 4 would be.
No, I said groups of 2 would be nice. 2 or 3 would be nice. 4 is too big, probably.
Okay. All right, well.
Check the video. Claire heard me. Yeah. So it seems to me like in a class of 9, 3 groups of 2 and a group of 3 would be good. 3 groups of 3 would probably be perfect. A group of 4 would then imply that there would then be another group of 5, or a group of 3 and 2.
Do the project, but they didn't want an A.
What's that?
I thought one person wasn't gonna do the project because they didn't want an A.
Everybody has opted for A's now, so everybody's in the mix.
What if we,
I just learned this yesterday.
so if we
Nine.
don't pass one of the like upcoming lit sums, does that mean we automatically like are, like so should we keep going with our like lab report, or this lab?
Well, if you bail on it, you're going to experience the ire and dissatisfaction of your classmates. But no, if for some reason you perform in a way that knocks you out of running for an A,
Yeah.
like you don't get exam scores up, or you fail a literature summary or something like that, because you have to pass all 4 literature summaries, then
Right.
there's no point really in continuing with the lab project. But that's really no different than when you get partway through evolution in college and one of the members of your lab group drops the class. And so the only difference is that that person who drops E&E doesn't ever have to face those people again. You in animal behavior have to face those people on a daily basis. My advice is make sure that you
Well, I
do the things that you need to do to get an A.
Yeah. There's no lab report on it too, right? So presentation.
Just a presentation. Yep, just a presentation.
I'll still keep going.
Not everybody passed the first lab, the first literature review.
Oh, okay. I thought you were about to say the lab
No,
report.
not everybody, I haven't finished with this.
Okay.
Not everybody passed the first literature review. The person who didn't pass the literature review knew immediately when we were talking about it in class that they didn't pass the literature review.
Okay.
Why? because the person knew immediately what part of the specifications grading they didn't accomplish. The specifications grading is there for clarity. You should, for any written assignment, be able to look at the specifications, go through that list,
Right.
and say,
So how is that person still in the running for an A?
because I'm way nicer than I should be.
Okay.
Okay. You know that we're all gonna take advantage of that.
Everybody has 3 tokens to use to
Oh, yeah.
convert a passing, or a failing grade to a passing grade if writing specifications are not made. Turn in a token, you move from a fail
say
to
Well, we
a pass.
can't use those on lab reports.
But you can't use those on
So
that.
if we
And if it-
fail a
and if
lab
it's a
report, we fail the
scientific-
whole class?
And you have to avoid scientific.
And if it's
You have to
scientific,
avoid
you're SOL.
Find scientific specifications. So you have these outs. So use your out, move on. So, but I'm saying the person knew exactly,
Yeah.
knew that they weren't going to pass and knew exactly what it was that caused them to not pass. The purpose of the specifications is you can take any written assignment that you write, put it up against the specifications, and you will know whether or not you're going to pass that assignment before you ever turn it in. As a matter of fact, I don't even know why I read them, because you shouldn't turn it in if you know you're not going to pass. And you have everything at your disposal to know whether it's going to meet the specifications, because the specifications are written down, they are clear, and they're not subject to negotiation. I would love to put a new specification on you guys about getting data to me in a timely fashion, but you know what? That wasn't in the specifications for the class at the beginning of the semester. So as a result, I can't go back and just retroactively do that, as much as I would love to.
I mean, can't you change the syllabus?
Don't.
One of them, one of,
I didn't know.
if you read about specifications grading and you do research on it and you read a book about it, which is something that I've done, one of the points of it is that you've thought about your class well enough at the beginning that you shouldn't have to be changing things at mid-semester. And the thing of it is that the whole point of it is to make things clear and predictable for you guys. And so changing things midstream wouldn't make things clear and predictable to you guys.
Alright, well, I'm gonna be outside your office.
I'm dealing with Logan.
The more that
How long
I
are you
hear-
gonna be here today?
I have no idea at this
Okay.
point. I have office hours at
It's like
2:30.
the longer the Paul
Alright,
speaks, the
2:30.
more anxious
I'll
I get,
probably be in
because,
at
like he says
2:30.
everything in the same
Why?
inflection. Because you say everything with the same inflection, so it's like hearing the same sentence over.
Have
and
you ever
over.
had
It's
somebody
like,
fail
oh my
this
God, oh my
class?
God, oh my God.
No, as a matter of fact,
Really?
I've had people make A's and B's, and quite frankly, this semester, I don't know why I wouldn't have nothing but A's in here. Because everybody in here is capable of making an A.
But it's-
I mean,
Yeah.
there are only 9 of you, and you're all just pretty damn good at what you do. Why would we not expect a bunch of A's in a class like this? And it isn't grade inflation, it's just that I'm asking you to perform at a particular level. I'm asking you to perform at that particular level in a consistent way. And if you perform at that level in a consistent way, then you get an A. If you perform at that level less consistently, you get a B. If you perform at that level even less consistently, you get a C. But you know what those levels are. They're spelled out in the syllabus. They're spelled out in the specifications. Satisfy the specs and move on. And in that way, it should be calming, not anxiety-made.
I wish it was, Paul, I wish it was.
When
I'll
you
see you
pass
out-
I'll see you outside your
it.
house.
See you out in 2 minutes. All right, let's see.
Couldn't get card installed, and additionally,
My
I had a
favorite-
question about how to dictate your working directory.
So let's see. Let's go.
I haven't done anything on this one, so I already need to save it.
I'm gonna close you out. And I don't know which version of R, and I don't know actually how to find is 3 years old.
See, the other day, when we were doing it for the Bean Lab report, I was like, hey, how do I update this? You're like, oh, just click the update button and it'll do it for you. So that's what I did.
Okay, all right, let's go. So let's go to are you using Firefox?
Yeah.
So let's go to, so you need to update base R. So let's go to the Crayon website. Crayon keyboard layout. Right, you're on Windows, right? So we need to change. Base R. Where did the downloads go?
It's still loading, but if you do that.
Oh, okay, there it is. That's where it's. It should be the latest version.
So since I'm downloading a new version, will I have to reinstall those packages more than likely?
Yes.
That's fine. It just-
But because you're working with a new version, it should go seamlessly.
I hope so. I hope so. Click yes.
Now, on a Mac, it would say you already have a version of R on your computer, you want this version to replace it, and you just click yes. On yours, when you're expected to go and find the older version of R, and delete it. It's not a big deal.
It's just easy to find where it is.
I mean, it should be in the program files. Assuming that your computer lets you look at program files, which it should. It's- it's- So we'll wait before it's finished doing its business. Because what it may just do is overwrite.
You wanna delete the old one, I don't know, those are the two old programs. You right click it.
That's actually just a desktop shortcut. That's
Oh,
not
okay.
an actual program. It's just, if you go down here, go to programs, let's see, it is. Oh, yeah, it's a desktop shortcut. It seemed like it was going to open up in a solution folder.
If you go to the File Explorer and then imagine it being downloads at the top.
So where are your files at?
Yeah.
Cool. Dark and stormy night. All right, there you go. There's that. Let me go back to Chrome Disk. So install packages is actually a command. So you can do it the way I'm doing it now, or you can just type in. Once again, it gives you an autofill thing, and so just put quotes ggplots 2.
my version was probably older than the version that car
So,
package was.
so what happens is, the packages are written by individuals because it's open source computing, and so two things happen. One thing that happens is that base R gets updated, and then it disables some functions of packages that it just doesn't interact with well anymore.
Mhm.
And then the developer has to go back and alter their package in order for it to interact with the continuous version of R. In some cases, when they then do that, it interacts with the new version of R, but it won't work on older versions of R. In some cases, people just don't ever go in and update their packages. And so, for example, on some people's machines, they'll have 3 or 4 different versions of R because they use packages that were older that haven't been updated. They won't run on newer versions of R, so they have to activate older versions of R in order to get it to run. That becomes a real pain in the ass. This is one of the difficulties with open source software, as opposed to software that's provided by a company that you pay a ton of money for. And so, the general rule is for most of